biological systems, if you lose the structure, you lose the function, the cell dies, the enzyme breaks down, whatever. So chemistry is the same way. You have to have structure. Good questions arose, you may not remember them from kind of the previous week when you were doing this, was how do we know something, or maybe why? Why does it have to fit this way? Like this has to come here and fit that dimension. And it's all based upon energy. So remember, thermodynamics governs the universe. Legitimately, whatever is energetically most favorable will occur. And that's not given, and that's given enough time, yes, but it's heading towards that direction. So is it more stable for the universe to be packed and ordered and structured very tightly? Or is it more stable for the universe to be random, chaotic, disordered? And the answer is it's random, chaotic, and disordered. More possible energy states for things to occur. That's what we're doing here. Okay, we've touched on valence bond theory. Use the valence electrons, pair unpaired, more stable to be apart, lowering the potential energy, maximizing stability. So that's VESPER. We need to discuss hybridization and molecular orbitals today. That'll tie in our bond character. Formal charge, and the big picture is of all the different types of structures you could draw, which structure contributes, now hear that clearly, the most to the overall structure. If you could draw 6 different types of structures for carbon dioxide, all 6 of those actually exist. Nobody's ever told you that, but they actually exist. Now, which one contributes the most? Like if you empirically look at the data, one structure will consistently show up, and that's got to be the double bond. That's formal charge. So minimize the number of formal charges on the atoms. And if you have to have a formal charge, you put the negative on the atom that has a greater electronegativity value. This does not actually consider electronegativity values at all. And that's a problem, because this is in some way totally bypassing a very, very important periodic trend. So electronegativity increases as you go up and increases to the right. So the desire for an electron is greater for the nonmetals than it is for the metals. And how does that impact chemical bonding? Because whatever wants the electron is going to move it closer towards itself, creating either an unequal sharing of electrons or a complete transfer of those electrons. And we'll discuss that here with the bond polarities in a second. And then oxidation states, as you've seen consistently before, fluorine versus fluoride. Everything wants to mimic a noble gas stability, not everything wants to be a noble gas. There's a big difference there, right? Be a noble gas means you've changed the number of protons. Mimic means you have the same electron configuration of a noble gas. So that's oxidation states. How many electrons do we need to add or remove to gain the stability of a noble gas? Bond enthalpies is now looking at all of this, like legitimately looking at everything above there. This is the question of now let's actually calculate the energies. And we'll do that tomorrow. So if it's not energetically favorable, then you personally have to do something to the system. You have to heat it up. You have to change the pressure, change the temperature, etc. If it's energetically favorable, then that reaction or that conformation might actually occur. So that's what we'll be looking at tomorrow. Okay? All right, that's kind of the big picture. Let's focus on these kind of 3 here, hybridization, molecular orbitals, and bond character. But to do that, we have to take another glance at electronegativity and bond polarity. Okay, here's a diagram. This is on one of the PowerPoints up there on the Model 5 up near the beginning. I want to show you this one. A little hard to see. The regions of coloration show the different levels of electron density. So the closer or the more electron density you have, we'll show that in the regions of higher color. So hot colors, oranges, reds, yellows, etc. The less electron density you have is going to put that near the cold colors, the blues, the violets, etc. Okay, so it's just showing the electron density distribution. If this is carbon dioxide, notice that one of the ways we, scientists, can actually end up showing how electrons move in a system is to legitimately draw, and for the rest of the year, you do not have to include these lone pairs in there. We should all make the assumption that all bonding atoms have a stable octet of electrons, meaning we could put enough electrons in there to be 2, 4, 6, 8. You know what I mean? So we can leave those out. We'll assume it has the octet. If there's supposed to be a lone pair on the central atom, we do have to put those in for the rest of the year. So central atom, put them in. Bonding atoms, you don't. All right, so we'll leave out the lone pairs around the outside. What this says is that if carbon is the lesser electronegative atom and oxygen has a greater affinity for the electron, then what we do is we draw this arrow saying shift the electron density towards oxygen and away from carbon. This is Greek letter delta. The symbol, I'm not exaggerating, it kind of looks like an integral sign in a calculus course, right? I'm exaggerating. That just means slightly positive, whereas the oxygen is slightly negative. So that's what the Greek letter delta means. Now, slightly means, legitimately, you just push the electron density a little closer towards the oxygen and away from the carbon. If this was completely positive and that was completely negative, what did you do? Or what did we do? If that's completely positive and completely negative, what would have happened? Don't overthink that. Yeah, if carbon had electrons and now it becomes positive, what did carbon do? It lost completely, right? And if oxygen was neutral and became negative, it completely gained the electron. You just created an electrostatic force of attraction between two oppositely charged atoms. That would be an ionic interaction, right? So slightly is actually very important here. Now, if that's it, if that's the only thing that was occurring, then you should see a net buildup of electron density over here towards the right side. So you could draw this density map and say, oh, look, there would be blue here and red over here, and over here would be no color, it'd be kind of neutral. Or in essence, maybe when we group this whole side, to say, oh, this is all positive and that's all negative. Anytime there is an unequal distribution of electron density, remember this word, polar covalent? Polar covalent means unequal sharing of those electron density, whereas non-polar covalent means there's an equal sharing of that electron density between two molecules. So think of it again as a tug of war. If I give Rachel one end of the rope and we're constantly kind of doing this, right? I mean, there's little fluctuations that are occurring. You can never stop those. That would be absolute zero, like Kelvin, when you stop these fluctuations. So there's movement. If it's a polar situation, Rachel pulls really hard. Oh man, I have to shift all of my density towards her. But notice my back foot is still there. I still have hold of the rope. I haven't let go of the rope entirely. Non-polar would be like, okay, I pull back, and now we're both standing up, and we're both just shaking like this, right? Okay, so that's equal and unequal sharing. If this oxygen is chemically identical to the other oxygen on the opposing side, meaning they have the same net number of protons, the same net number of electrons, then they're chemically identical in every way, then the electrons that were with this carbon are not any more likely to go to the right than they would go to the left. Fair? You have two equal atoms on both sides. The question is, why do they have to go right? They actually don't have to go right. They could end up going left as well. So this is showing that both oxygens are actually slightly negative. In science, it is actually a little common, and don't write this is wrong, that if we put a little tiny delta sign and a big delta sign, that means this gets more of the electron density, and this gets less of the electron density. But if in general we draw those two delta Greek letter signs similar, then there's an equal distribution of that electron density. So therefore, carbon dioxide is a non-polar molecule. It actually has an equal distribution of electron density. So how do you focus in on that? Literally look for symmetry. If things are 180 degrees apart and there are two chemically identical atoms, then this molecule is symmetric, then therefore that is a non-polar molecule. The downside of doing it this way, legitimately, so that's correct, and I would accept that answer, non-polar, 100%. I'm on board with that. However, empirically, carbon dioxide actually exhibits more of a polar nature in general, because one of these double bonds actually ends up going back towards the oxygen. You don't need to know that, but if you're looking at why carbon dioxide is actually called a greenhouse gas, it's literally because it's a polar molecule, not a non-polar. I say that to you because if you go to the internet and type in is carbon dioxide a non-polar molecule, you're going to get yes and you're going to get no. It's not. So what do? For this class, if it's symmetrical, you say non-polar. Okay? All right, let's do one that's not symmetrical. Consider hydrochloric acid. Again, we can leave off all these lone pairs around there because we're assuming there's an octet of electrons around the bonding atoms. Check here. Who wants the electron more, hydrogen or chlorine? Chlorine. It's higher up, it's a halogen, it wants that electron density a whole bunch. When it pulls that electron density away, it makes this hydrogen slightly positive, and now you have an unequal sharing of that electron density. You have a net buildup of a region that's positive, a net buildup of a region that's negative, and that's now called the polar covalent bond. So this is what you're deeming, this bond here, this is polar covalent, right? Polar covalent bond. Can you think of anything else? What if I showed you something like, let's say this, carbonate. So negative charges would be here, leaving out all the lone pairs. Polar or non-polar? This is definitely harder. This is not a general chemistry question. This is definitely Chem 2.
Non-polar.
Okay, why would you say that?
Is it symmetrical?
Perfect, and that's fine with me. It is non-polar because there is symmetry. These bond angles are 120 degrees, right? All the way around. That would be a trigonal planar molecule. Now the question is should there be some electron density that shifts towards one oxygen more so than the others? As shown, yes. Which oxygen has more electron density? As shown. Yeah, the one with the double bond, right? So if I was going to draw a big delta sign, then these would all be little delta negative signs, right? However, what's keeping this as a nonpolar molecule? Even though that's true, what happens with the double bond? Where can it go? Any of them. So the resonance hybrid structure, remember that? When you say what's in common with each one, you get something like this, where now you share that double bond character over 3 different oxygens. And neither oxygen, none of the oxygens are going to get more of the electron density than the other if they're all chemically identical. So as long as you're bonding to the similar atoms that are symmetrical, you have a nonpolar molecule. What would it be if you did something like this though? Polar or nonpolar? Polar. That's not symmetrical. Who wants the electrons more, oxygen or sulfur? Oxygen does. So this side of the molecule is now slightly negative, and this side of the molecule is going to be less slightly negative, right? Yeah.
What about H2O?
H2O, water, perfect. Polar or nonpolar? Based on the arrangement. And I'll put the lone pairs in the central atom.
Non-polar because it's symmetrical.
It does look symmetrical, that's fair. And the only thing, and to your good point though, because I haven't mentioned this yet, are these electrons up here part of our discussion of polar or nonpolar? And that is a yes. Okay, so what does that ultimately means is look at how much electron density is up here on oxygen compared to the electron density down here. The electron density near the bottom is basically, or is, no lone pairs on the bottom side of that oxygen atom. All the electron density is shifted up towards the top, if you will, making this slightly negative. And this area is slightly positive near the bottom of oxygen. So there's a separation of charge there. Water is a polar molecule, and if it wasn't polar, legitimately, we've said this many times, your Earth, legitimately, fundamentally, your biological systems, anything that requires water would look totally different. Life would not exist. Earth would not be Earth anymore if that was not polar. There is an idea, it's called likes dissolve likes. This means polar dissolves polar. Nonpolar dissolves nonpolar, right? What about ionic compounds? Well, you could say polar molecules are very similar to ionic molecules. So polar dissolves ionic sometimes. Do you remember your you remember at some point you had a solubility rules. I saw it on one of your yellow sheets back from a fever or somebody. That you had things like this, all nitrates are soluble when you put them in a solution of water, but if you take a lead ion and you put it with chloride, it precipitates out and turns into a solid. That's basically what you did with your silver mirrors. When we shook it all up, we're putting precipitates on the side. So not all ionic compounds are soluble. This is just a general guiding principle. Likes dissolve likes. The movie, Wizard of Oz, remember in there, The Wicked Witch of the West? Remember in one scene, you remember this? You guys are too young for this? The Wizard of Oz, do you know it?
Okay. I know the Wizard of Oz.
Yeah, good.
Yeah.
Just making sure, it's good.
We haven't heard of it.
Yeah, I don't remember which part, but the Wicked Witch of the West ends up melting. she say melting or dissolving?
I'm melting.
I'm melting. If that's true, then
I'm dissolving.
from a, that's what I think in my mind. I'm
Dissolving.
dissolving. If she's melting, we know that's a phase change, and melting and freezing, is this overthinking what it was? Probably, but I think it's, remember this, like legitimate, I won't worry about the distances. If she's melting, she's here, and that requires some amount of energy to do that. So she's absorbing energy? Right. You're absorbing energy? Like, where did that energy come from? We don't see any influx of thermal heat energy. Maybe it's just the joy of, what's her name? Dang it. Is it Gloria? Dorothy! Dorothy.
Oh,
It's
Dorothy.
Dorothy. I don't know. It's been 30 some odd years. Maybe Dorothy's excitement provides the energy. I don't know, but she can't be melting.
Doesn't she splash herself with water? Maybe it's boiling.
But if it's what, that's what it was. That's why I thought dissolving, right? Was it water, right? Yes. Then, therefore, you're asking the question, if the human body is polar, made up of large quantities of water, if you personally dissolved, you would have dissolved in the shower many, many, many days ago, right? Because water's polar, you're polar inside, and you should have dissolved, like legitimately dissolved.
Maybe we should be asking the question, is the witch human?
That's a deep question too.
Oh, would it?
But then we could do hydrophobic. So go to the real life situation and say, why do you not dissolve? Every time you wash your hands, take a shower, why are you not dissolving? I mean, your skin cells fall off, but that happens anyways.
Because we're not polar?
Externally. Right. Externally.
Doesn't that
Internally,
drinking water, though?
you're 70%. What'd you say?
What about drinking water?
Like when you drink it.
Yeah, 70% of you inside should be dissolving, but it's mixing with the other water. So all of your organs and tissues are hydrophobic, and that's a great thing. Because when you drink water, your insides don't turn into a goo, right?
So
What
all of
it-
our liquids are polar, but the tissues of us are not.
Yeah, what component of the tissue is hydrophobic?
The
Biology.
tails.
What?
The tails, the phospholipid tails things.
So you have, right? What do you call that? You said it. Phospholipid membrane, right?
Yep.
There it is?
Yeah.
Yeah, okay. God, biology, you have to write so much just to get a point across. Wow, right? Here, hydro,
Philic. Phobic.
which one?
It's philic. Why
Philic
didn't
or
you write?
philic?
No, it's
The
Philip.
outside is phobic.
Which one?
The outside's
Hydrophilic.
Philip.
What's out here? This is your blood plasma.
Of the inside.
This is intracellular, so this is all your mitochondria, matrix, etc. So this,
Hydrophobic.
Is it?
Are they backwards?
this is for the short version. All right, there's your phosphate group head, lipid tail, so phospholipid membrane. Do that going this way now as well.
No, he's got that. He got that.
All right, then a whole bunch of carbons going this way. Now go.
Hydrophobic on the outside and hydrophilic on the inside.
These are all nothing but carbon and hydrogen, so let's look at one of those.
Are we wrong? Oh my god. I don't know.
We're just going for the Y. That's what we're going for. We're trying to rationalize the Y.
Okay.
Polar or
because,
non-polar?
non-polar.
Non-polar. Will non-polar dissolve in polar?
No.
So these are hydrophobic.
Oh my lordy day.
Phobic.
Exactly.
I knew it. It was hydrophobic. That's.
Yeah.
The tails are hydrophobic.
These are hydrophobic. And then up here, these are hydrophilic.
But what is just these building up?
No, see, you guys don't know.
That just happened.
What do you mean?
Oh yeah.
Just like a lot.
Like cross-curricular instruction.
But if it's
Yeah,
hydrophilic.
but what if we didn't do
Oh,
that?
I just, what do you mean?
I don't know, it just fell apart.
Oh, okay. I was just trying to say the Wicked Witch
No,
of the
I'm not
West.
saying I didn't understand it, it's
No,
just
no, no.
like a lot.
I'm just saying the Wicked Witch of the West should not have dissolved. You know what I mean? Like it
After
couldn't-
all that
she
silica?
could. She can't melt, she can't dissolve. It doesn't make any sense to me. I can't
For
watch
that
something
whole
you do.
tangent, you just
Wait.
wanted to say that the way kid
Wait, which one was?
She
She couldn't dissolve based on polarities. It doesn't make sense. If she was an ionic compound,
It's
I would have been with her. I would have been like, you're
Is
dissolved.
she just salty? Like sodium.
That's
Ooh. That's deep.
That's
deep.
That's
Also, you have to consider she's a witch, right? So
Yeah.
they probably don't shower, and maybe that's why she's just green.
Yeah,
And that's why maybe people don't like her.
she was swimming too much. She got that chlorine bleached hair.
No, she
Oh.
can't swim because they don't know.
She
That's the
dissolves.
point.
Ah, Hollywood got us again.
Maybe it wasn't a bucket of water. Did they ever say it was a bucket of water?
They didn't. Maybe you're right. Maybe it's an acid.
Oh.
That would have been good. Oh.
That's an extremely strong
did
acid.
they? I
If
think
it's
we
not
need to watch
put in the
this movie
bucket,
just to
I'm
make
sure.
sure.
Yeah, we
I
should
said
watch
it
it in
in-
class.
yeah, we should watch that.
Yeah,
Yeah,
I think we should examine it.
Yeah, we do.
Oh my god, it's your notepad.
It's my notepad.
The thing that you had outlined.
Yeah.
Can I have it?
It's amazing. It just has, yeah, you can. It just has bullet points. All right, write these down, and then get out your fancy Pyrrhic table.
Is that a
0%?
I'm confused.
Wait, is that?
Oh my. What the heck? What are you doing?
Yeah, you're gonna use your fancy Pyrrhic table.
Well,
What
it's
does
already
that
out. You did not need to give
Wait,
permission
what
for
do we label this?
Electronegativities.
Don't we have a little thingy for that?
You do.
that? Should this be like on a whole separate thing right now?
Trust me, my memory is gone.
Everything's gone.
We have a paper for it.
So much good stuff.
Hey, you gotta move so I can see what I'm supposed to be writing down.
I'll throw my back out on that one. All right, you need your fancy Pyrrhic table. Look at the very back top of it.
Okay, you gotta do one thing at a time.
Okay. How do you do that?
Just stand there.
Okay. Like this?
Yeah, we'll say you when we're ready.
Okay, how about now?
It's cause you move on before we're done.
I know, there's so much good stuff. We
And
have
then-
so
and
much.
then you get really confused later.
You're doing great.
I
You're
can't
sticking
tell if
with
these are numbers or percents.
percents.
They look like numbers
What do you mean?
sometimes.
These little ladies? My
Yeah.
eyeballs?
Like, I don't know.
Does
Your
it?
eyeballs?
Yeah, they look like, it looks like a nose.
What? Oh my god, no, that's not what I said. Mr. Morgan, can you move?
I screwed everything.
Can you move?
That's percent.
Thanks. Oh,
Why are there two smiley faces in one? Like you don't.
Oh, yeah. Boogers.
Oh my
Ew, what?
Snot rocket from a 5-year-old.
Specifically a 5-year-old.
Yeah, I mean, it's what happens all the time. Oh man, bless their hearts.
Does
1-year-olds
that
and
say
2-year-olds.
5.1?
What's the front?
Very top, at the back side, look up there, it says percent ionic character of single chemical bond. Okay, here's the big picture. We're only dealing with single bonds, not double or triple bonds, or things don't work out this way. There's two rows. There's difference in electronegativity, and then the percent ionic character. That's what you're looking at here, is the percent ionic character. It honestly doesn't matter to me which row you look at, because there is an endpoint. Like, for instance, if you look at 50% ionic character, that corresponds to what, 1.65-ish difference in electronegativity. So at that point, now you're an ionic bond. So we need some electronegativity values. Down here on the bottom left of the back side, if you look at where my finger's at, there's a little scale, a little legend here. That legend tells you where at in the box is the electronegativity value. So we're looking at the upper right shaded dark area. Isn't this an amazing periodic table? There's so much going on here.
Exactly.
All right, let's look at fluorine. Fluorine has 3.98 electronegativity. And let's do hydrogen. Hydrogen is 2.10.
That says,
2.2.
yeah, that says 2.
On your periodic table?
Yes. On hydrogen.
Mine says 2.1. Did I give you a new version?
Just 2.20.
It
You're
says
right.
2.20.
Mine says 2.1.
No,
it definitely does.
Yeah.
Yeah, that's weird.
Alright, well, I'll use yours. You tell me, is this the same then?
Yeah.
Okay. Alright, so 2.20. Alright, the difference here, go ahead.
1.78.
Go up here. Yeah, good. 1.78, that's the difference in electronegativity. So find that on the top row. Top row. So that's the difference, 1.78. Are you ionic? Oh, I chose a bad example. Or are you going to be pure, polar? Which one of these are
Sure,
you?
it'd be ionic.
Ionic. It's okay. It's the
greater.
same. It's 51, 55.
Yeah, it's pretty darn close. Hard to tell.
It's
But
still 50%
But it's still greater than
I
50.
think it still holds a 50. The ionic character here is,
It's 51.55.
I think officially it's a polar compound though.
What?
Yeah. So let's
Ain't
do
no
next
way.
one.
Yeah.
I know, I chose a bad example. Let's do
Why is it polar?
CO2.
Wait.
Why is it
Why
polar?
is it polar?
Officially, empirical data will say it's polar. It doesn't exist as
Ours
H
isn't
plus and F
specific
minus.
enough to the decimal point.
Yeah, it doesn't. This doesn't exist like that. It exists as a covalent bond.
He's just using random
I was doing a
examples
random
to get
example.
the concept.
Let's do
I'm so
carbon.
confused.
Carbon.
I'm so confused. How is this
And
1.78?
oxygen?
Yeah.
Carbon dioxide.
CO2.
Or are we doing carbon
So
monoxide?
for oxygen, I get 3.44. Is that what you have?
Uh-huh.
And for carbon, I get 2.55.
Yeah.
Okay. Greater or less than 1%? No, or percent, not percent. Greater or less than 1 difference in electronegativity. Less than 1. So if you go up to there, are you greater or less than half a difference in
Less than
electronegativity?
Greater than
You're
half.
greater than half. So you're between 0.5 and 1 as a general reference frame. Is that corresponding to the percent ionic character of nonpolar or polar? This would be homonuclear diatomic, so like H2O2, N2, etc. Okay. Are we here or here for CO2?
Not polar.
I think if we're officially, what is that,
I think it's 0.89.
0.89 gets us 0.9. I get 19%,
We're still
20%, which puts us in here.
I'm so
Polar.
confused
Didn't
by
we
this
say it
number.
was non-polar?
Can you like?
Symmetrically, yeah.
Explain
Remember we
how
said
you
because
use
it's a
that.
greenhouse, the internet's going to tell us it's polar. So the carbon dioxide percent ionic character comes out to be here. So you calculate the difference in electronegativity, and then based on where that's at in the row, you drop down and look at the percent ionic character. Based on where those percent ionic characters are is where you classify the actual compound. So it's just a tool. It's a tool. You can use symmetry as a reference frame, or you can calculate the electronegativity differences. Both, ideally, should get you to the same outcome of either polar or nonpolar. However, this is definitely empirical, and the other one is just based on symmetry. Which one should you do? I'm fine with you doing symmetry, but this is also a good way to do that. Okay. All right. Now we're ready to talk. Get into our hybridization of molecular orbitals. Here it is.
Hold up.
Yeah.
I'm a little confused. Before you erase anything, so wouldn't it matter more on shape than like? So wouldn't you only do electronegativity when you're talking between like two different like specific atoms?
Yeah.
So instead, but the whole molecule itself, if you want to determine whether it's polar
Yeah.
or non-polar, you have to look at shape, right?
You have to do everything. Yeah, so to your point, what actually exists, you have to do everything. So you have to calculate formal charges and electronegativity differences, and you have to look at the symmetry, which would be Vesper, and you have to do all of the above. So there's no single, and that's why we've left up here for so long. You can't actually just pick one out and hold it and be like, oh, that will tell us what our molecule looks like. In gen chemistry, you actually do, and that's fine, because we don't need you to look at all 8 of these all collectively together. So which one do you do? For me, I tend to default to the symmetry. That way I don't have to go back to a table all the time and always calculate the electronegativity differences. It takes time, and honestly, symmetry often is pretty stinking close. So plucking that one out and looking at it. So default to symmetry over electronegativities. But a perfect example of that would have been our carbon dioxide. Based on symmetry, it should be nonpolar, but based on what we just calculated, it should be polar. So what does it actually exist in real life? Both of those exist, both the polar nature of carbon dioxide and the non-polar nature, but the polar wins out empirically. Data tells us it wins out, right? Gloria, what was your question? John Wayne, what was your question?
You answered mine.
Did I? What was it though? What did I say? Did I say something?
What are you looking at me?
Because you're looking at me.
You're
You
freaking.
started it.
I'm
No,
looking-
you started it. You were talking.
I'm looking at you,
Person.
looking at her, looking at you.
Okay.
So what's our question?
I don't know. All right. Okay, let's do hybridization. It's not so crazy. It does pull up why Gen Chem has exceptions. This is the atomic orbital. So just electron density of hydrogen, the electron density of another hydrogen coming together. Notice that there's some overlap, and wherever you get overlap, you get a sharing of electron density. A covalent bond occurs. If that electron density is shared equally, nonpolar. If it's unequal, polar. So is this equal or unequal sharing of that electron density here in the middle? Equal, right? So it's nonpolar. What are the black dots supposed to represent? The nucleus, measurable. You know the protons there, they don't move a whole lot. Lots of mass there. Okay, chlorine. What sublevel might this represent? The pink. That's the P sublevel, right? So one of the P sublevels of chlorine interacts with the S sublevel of hydrogen. Is that okay? Is that predictable based on the orbital diagram of chlorine? So this would be 3P. I'll just do the valence shell of chlorine. Is that okay? That this P sublevel of chlorine would want to interact with the 1S sublevel of hydrogen. So can those two electrons share? Yes. Nothing wrong there. Is this still okay that two chlorines can interact together via that open spot here?
Yeah.
Yeah, that's also still okay. Now remember when we said something like this, beryllium, which is a 2S, 2, VeF2, beryllium difluoride. If this, is this fluorine? Could this be fluorine? We need to change something. What should we change? For fluorine.
Oh, orange, just turn it down to 2, right?
Okay, so it's just the 2s. So we need one electron. That's fine. Beryllium has 2 valence electrons that it can share with fluorine, that each needs 1. But based on this alone, does it look like beryllium has any open sublevels to share electrons with? The answer is no, right? So now in general chemistry, you would have been like, oh, there's an exception, and it's okay, things have exceptions, just remember BEF2. Now we say, no, that electron can sit here. Okay, why? How did we say it could do that? Why did we take one electron from the 2s and move it to the 2p in general?
Because they overlap.
Yeah, they're both in the second energy level, right? That means they're close in energy to each other. This is just slightly higher because it's a P sublevel instead of an S, so it doesn't take much energy to move it there. Now you can dump a fluorine and a fluorine into there and create 2 bonds to create your beryllium difluoride molecule. Okay, if that's the case, now that leads to the question of what is that really? Like what notation, what words do we really use when we dump an electron to a higher energy state? And it's called hybridization. So consider this, there it is, there's our 2s electron, forget the 1s, it's not doing anything, we're just doing the 2s. If we move one of those 2s electrons into the 2p sublevel, we now call it a hybridized orbital. Okay, there's a major point here that we want to get across. The number of atomic orbitals that participate in hybridization is equivalent to the number of hybridized orbitals created. So number of atomic orbitals used is equivalent to the number of hybrid orbitals created. Okay. All right, so what does this mean? If we're drawing a potential energy diagram for beryllium, here's the 1s, the 2s, 2p. Okay, the core electrons don't do anything. This is what it would typically look like. Now, if we hybridize means mixing the s and the p orbitals together. You actually mix them. if we take one of the S's and we take one of the P's and we hybridize them together, we created an sp hybridized orbital. Okay, that's what that means. We'll take one of the S, one of the P's, mix them together, and you call an sp hybridized orbital. But notice we took one atomic orbital and mixed it with a second atomic orbital. So there's two atomic orbitals used. That means we have to create two hybridized orbitals in the process. So now we would just say there are two sp hybridized orbitals created when you mix two atomic orbitals, one from the 2s and one atomic orbital of the 2p. Now, in general, what this means is the 2s is no longer there because we've mixed it, and the 2p no longer is in essence there as well, except for one position, two positions of there. So let's do this. Let me keep in. Sorry, there's a whole bunch of lines that are moving. Let me try to draw it with a different color. When we mix these orbitals, they're going to come out to be right here. They're going to be greater in energy than the 2s. They're going to be lower in energy than the 2p. So this is the sp hybridized orbitals that were created. Notice we took one atomic orbital and a second atomic orbital, and we created two hybridized orbitals that are lower in energy than the 2p and higher in energy than the 2s. Did we, in essence, conserve the number of atomic orbitals? How many should we have had if this was just a regular orbital diagram? 1, 2, 3, 4. And now we have 1, 2, 3, 4. We've conserved that many numbers. All right, so now we'll start mixing things together. What geometric shape is this? Give me the molecular geometry of BeF2. Molecular geometry. Linear. So SP means linear. SP2, trigonal or trigonal planar.
Okay, I have a question,
Yeah.
Mr. Morgan. Wouldn't this be an ionic bond?
Yes.
So why are we?
Just to make the point. Yep, that's it. But you're right. We could calculate the electronegativity. I don't know what that would come out to be. Fluorine 398, beryllium. Yeah, it's well into the ionic. So even electronegativity values would tell it's ionic, and even based on our electronegativity ideas that the fluorine wants these electrons more than what beryllium wants this, that would create a 2 plus and a minus 1 charge. Yep. So true, we're just trying to make a point of what hybridization means.
So this wouldn't actually happen. For beryllium?
Not in the truest sense, no.
Okay.
Yeah.
This
Yeah.
is for other things.
Go for it.
For your number of atomic orbital, like your equation at the top, what is it? Like, what is it? Is it adding, or is it just the number
Nope.
of atomic
Yeah,
orbitals?
so this means that you took one of the 2s and one 2p sublevel, and you made two sp hybridized.
But like your word, so it's like the number of atomic orbitals used
Used.
hybrid?
Used to hybridize in hybridization.
Okay.
Sorry. Is equivalent to the number of hybridized orbitals created. Yeah. So let's check. Let's do same thing, but let's try for boron. 2s, 2p, BF3. Boron or not boron? Boron or not boron? Is this boron? Yeah, sorry.
Yes.
Yeah,
Yeah.
okay. Notice that it looks like boron can only make one chemical bond here in order to pair. So how is it even possible to have 3 fluorines that are there? We're going to take this electron and make it look like it's right here. But in doing so, we took the S sublevel and mixed it with, not this P, I know it looks like that, but these are chemically equivalent, right? In terms of their energies, look at what they've done. So follow them back here, those are degenerate orbitals. So we've taken one of the S's and we've taken 2 of the P atomic orbitals, mix them together. So that's 3 over here, 1 S and 2. P's to create 3 sp2 hybridizations. So where in energy should those be? Apply the same tactic. Should the hybridized orbitals be greater than the 2s? Because they have some p character. Should the hybridized orbitals be less than 2p? Yes, because they have some s character as well. So how many total orbitals should we have? Notice that was 1, 2, 3, 4. We need to keep the 4 that we originally started with. This is sp2, this is sp2. We mix 2 of these so they go away, and that's still one of the 2 p's. So notice we have lost our 2s sublevel. This is, if you want to call it energy level, this is still the second energy level, but the sp2 hybridization, and there are 3 of those.
Okay.
Sorry, 3 of those. 3 of those. There's our 4. 1, 2, 3, 4. So here's what we would do. We say this is sp2 hybridized, this is sp2, and this is sp2 from boron. Should draw those a little better. Okay. And then let's draw that like this. So here's the sp2 hybridization of boron, and then the atomic orbital of fluorine. I'll just draw as a circle. It's not, it's a p. Maybe I should draw it as a p sublevel. And this is the atomic orbital of fluorine as well, and the atomic orbital of fluorine. So notice there's some overlap. I'll shade it in. Wherever that overlap occurs, there's a covalent bond. So we took 1 atomic orbital, 1p atomic orbital of fluorine, and overlapped, allowed a covalent bond to occur with 1 of the sp2 hybridized orbitals of boron, where there are 3 hybridized orbitals, and each of those are mixing with the p atomic orbital of fluorine. Go for it.
So where are the electrons in the like potential energy graph?
Yeah, you'd still dump them in there. Yep, absolutely. So we're still going to be dumping it in. Don't draw this. Hang on. Wait, before you draw this. We need to draw what's called a molecular orbital diagram. So hold off on where the electrons go, but we're still going to dump them in there. That's coming up right now. So the numbers and where at, that's coming up. Yeah.
Where does the 2 from?
Where-
SP2. Is it because it's in the second
You
energy?
took 2 of these p's, right here, and you took them away and you mixed them with the s. So that's 2 of the p atomic orbitals mixing with 1 of the s atomic orbitals. Yeah, so the p3, what would that mean? What's this 3 mean? Because this is implied 1. 1, 2, 3. What's that 3?
You used all 3 of
Yeah,
the-
you took all 3 of the p orbitals and mixed them with the s. Give me an example of that.
Carbon and fluorine.
Okay. Carbon, CH4, would be 2s, sorry. And 2. Okay, how many bonds? This is the orbital diagram for carbon. How many bonds could carbon make based on what this looks like? 2. 1, 2. We need to be able to make 4. So we're going to take this electron. We said make it act like it's here. And in doing so, it mixes with these 3 degenerate orbitals that are all equivalent energies. So you take 3 p orbitals and you mix it with the s orbital. That's this. And is the molecular geometry of carbon tetrahydride, or methane, is that tetrahedral? Yeah, molecular geometry is. So I think the simplest thing for you to do legitimately is almost to just memorize this. I think that's sufficient. If the molecular geometry is tetrahedral, it's sp3 hybridized, almost always. If it's trigonoplanar, it's got to be sp2 hybridized, almost always. What do you think about this? What if I have oxygen? What is the hybridization? Forget whatever bonding. What's the hybridization of carbon?
Trigonoplanar.
So it's a trigonoplanar because 1, 2, 3 regions of electron density. So what's the hybridization?
SP2.
It's sp2. So this is going to be one of the sp2s, this is going to be a second sp2, and this is going to be the third sp2. And now the question of what's that double bond thing, right? Because if you have 3 regions that are bonding sp2, what about that guy? That's now coming in and leading to Gloria's question of where do the electrons dump into? And we're going to talk molecular orbitals. So let's try to answer this question now. What's that double bond? Okay, here it is. All right, Greek letter, sigma. Just draw it as an O with a little curly top on there. All right, if you have what's called an internuclear axis, typically for us, we'll call that the Z. So in 3 dimensions, X, Y, and Z, that's fine. This would be the, what does inter versus intra stand for? ER versus RA. So interpersonal communications, intrapersonal communications.
Intras with the
Perfect.
between.
This is how you think, how you process. This is between 2 people, their interactions. The smile, oh, I receive a message. Oh, I frown, I give a message back, right? Okay, so this is between 2 regions of electron density. If you drew a line straight through those, that's the internuclear axis. We'll call it the Z axis. Okay. If there is a bond on the internuclear axis, this is called sigma. So sigma bonds occur along the internuclear axis. Pi bonds occur perpendicular to that internuclear axis. Okay. So notice this is overlap of 1p. This could be like fluorine, and this could be fluorine. The atomic orbitals of fluorine can overlap, that's this region. If they overlap along the axis connecting the atoms, it's a sigma bond. If the overlap occurs perpendicular to the axis for fluorine and fluorine, notice here's still our general shape of P, that's here, like this. And here's the overlap of electron density occurring between there. You call it a pi bond. So sigma along the internuclear axis, pi perpendicular to the internuclear axis. If instead, along the sigma and,
Wait, can you go back?
Yeah. Which
Yeah,
one?
The one you just.
So on this one.
Yeah, just give us like 2 seconds.
Let me show you this next one as well. It's the same thing, just for the.
What's the name of this,
Sigma.
What is that? What is this one called? This is molecular geometries and bonding. Okay. All right, let's look here for a second. Okay, looking at this oxygen, this is going to be a little weird. We said this carbon is sp2, sp2, carbon sp2. Okay. Looking at just oxygen, how many regions around the oxygen? Regions of electron density around oxygen. 3. 3 is sp2 hybridized as well, right? So now we have sp2, sp2, and one of the sp2 hybridized orbitals here mixing additionally. So that takes care of oxygen and carbon except for that double bond. This double bond is different than these bonds here. So these bonds would be sigma, and this bond is also sigma, and the other one's pi. Okay. Just looking at that, what can you tell me? I haven't told you. What can you tell me about the sigma and pi bonds? If we were trying to put this molecule on a piece of paper, what would we notice? So carbon and oxygen. Would this sigma bond be in the same plane as the paper? What do you think about that? So stick carbon here, oxygen, oxygen, oxygen. Yes, then the sigma bonds are going in the plane of the paper. Where's the pi bond at? It's up here somewhere, right? So carbon is sending some electron density up, oxygen is sending some electron density up, and then those electron densities are overlapping up here, which is perpendicular to the plane of the paper, or the internuclear axis. So what you need to take away from this is single bonds are sigma, double bonds are pi. Single bonds are sigma, double bonds are pi. So you're memorizing this in essence: linear, trigonal planar, tetrahedral. Sigma bonds are single, double bonds are pi. Okay. What about a triple bond? What would that be? Don't overthink that. You only have
Something else.
could, but we only have two different types. It's just another pi bond. Let me see if I have a picture of that. I do. Okay. Acetylene. Oh, sorry. It's gone. All right. Here it is. See. Okay. What is the electron pair geometry here? Electron pair geometry. Linear, trigonal planar, tetrahedral, and it's linear. You have one region, two regions. So what's the hybridization here? Okay. If it's linear, it's got to be SP. So this is SP hybridized. Okay. If you mix an S and a P together, how many SP hybridized orbitals do you form? Two. Take an S, take a P, that's two. You have to create two. So here is one of the SP hybridized orbitals of carbon. Let me draw it like this. Where's the other one? Don't overthink it. Okay, it's one of these bonds. So there's an SP. What type of orbital is hydrogen overlapping with carbon? Is hydrogen hybridized, or is it using its atomic orbital that's unhybridized? It only has one electron in the 1s. Can it overlap with anything? It's just the 1s atomic orbital. So let me draw that like this. And say there's some overlap there. This is the 1s atomic orbital. Okay. What's the electron pair geometry here? Electron pair geometry. Still linear. So what's the hybridization? SP. And how many hybridized SP orbitals did we create? S and P creates so two atomic orbitals make two hybridized orbitals. So here's one of the SPs. Here's the other SP. What's this orbital? That's the 1s. Okay. All right. Let me draw this a little bigger because it's overlapping here, and this is overlapping here. Okay. What type of bond is this? Sigma or pi? How do you know?
Single bond?
Because it's a single bond. What about here?
Sigma.
This is sigma because it's
Single bond.
single bond. And over here?
Sigma.
Sigma. It's a single bond. Okay. We know bond because it's a covalent compound and it's overlapping. Now, this guy here,
Pi.
that's pi. So a double bond is pi, and this guy is also a pi as well. So perpendicular to the axis. Maybe the coloration isn't, I don't know, it doesn't always help me, but maybe you can see it better than I can. Here's the internuclear axis between two carbon atoms. Can you tell that there's definitely some overlap going up? Where's the other overlap going? Up and down. Where's the other one? Towards you, right? Can you kind of see that a little bit? This area here is kind of going back and forth into the board, and this area is going up and down. So if this is the axis, up and down, that's a 90-degree angle. And in front of you, that's also a 90-degree angle with the internuclear axis. So each of those bonding that occur perpendicular to the axis is a pi bond. In general, is a double, triple, or single bond, in terms of strength, who's the strongest? Triple's the strongest, because more density is overlapping. However, if you had to break any one of these bonds, is it easier to break a sigma or easier to break a pi?
Easier to break a pi
Why is that? You're right.
because it's not.
It's not hybridized?
I mean, it's kind of a poor analogy, but if you're playing tug of war, don't you connect the rope between two people? That's really hard to like rip the rope out. How would this work? Take a strand of that rope and send it vertically, and then you're playing tug of war here, but you have a little piece of that rope that you're just going to tug on perpendicular. You know
It's
what I mean?
off balance.
Yeah, it's not. You're not pulling in terms of vectors and physics.
Oh,
You have a totally different amount of force here as the vector component here is. So easier to break a pi than a sigma. However, collectively, triple bonds are stronger than double bonds, which are stronger than single bonds. More electronic character being shared in a triple bond. All right, let me put up one molecule here and you take a guess. You and your partner go after it here. All right, you guys got to list out in a similar way what we just did here. Try to do this. Yeah.
This.
What is that? That's what's going on. All right.
Great.
You got this.
No.
You're just
Yeah,
drawing
this
I
random
believe in
things
you.
on there.
Why
Okay.
did you keep going? Like, that's a lot.
There's symmetry here, though, right? Ish.
No.
Ish.
No,
Ish.
not really.
Ish.
I mean, you have the same elements.
All right.
Yes.
I'll start.
Okay, thank you. Thanks. Yeah, you should do that.
Carbon.
Is that it?
Atom.
Is that it? Thank you.
No, I mean electron pair geometry of carbon.
Trigonal planar.
Okay. What's the hybridization?
SB.
SP2.
Okay. So we're gonna say sp2, and then did I draw that up? Yeah, I did. Did I? Yeah. There it is. And then this is one of the sp2s. This is the second one. Where's the other one? This is the third one. So we have sp2, sp2, sp2. Right? That's going to be chaotic to write all that in there, isn't it? We'll try it. And then what's this hybridization of oxygen? We just did it. Trigonal planar. So this is also sp2. So sp2, sp2, and here's the other sp2. Is this a sigma or pi bond?
Sigma.
That's sigma, single bond. What's this one?
Pi.
That's pi, right? Here,
Sigma.
that's sigma. This one,
Sigma.
that's also sigma. What hybridization?
Tetrabutane.
So hybridization would be
SP3.
sp3. 1, 2, 3, 4 sp3 hybridized orbitals. If these are overlapping, what type of bond?
Sigma.
Sigma. What type of bond between the atomic orbital of hydrogen, 1s? Here,
Oh.
that's sigma, still single bond, right?
Okay.
So you just want to know which ones are sigma and which ones are
And the
pi.
hybridization of those, yeah. So keep hybridizing, keep calling things pi or,
Wait, so then what do you mean by hybridizing? Like, is the SP2, like, just which one it is?
yeah, so you have one atomic orbital with two p's creating 3 hybridized sp2 orbitals. 1, 2, 3.
So you want the pi
So-
bond that doesn't have a hybridization?
Right, that is an unhybridized p orbital, atomic orbital. Unhybridized p atomic orbital of carbon interacts with the unhybridized p atomic orbital of oxygen perpendicular to the internuclear axis to create a covalent bond. I feel like we should simplify this. Can we? Atomic versus hybridized? Okay, 2 columns. So can you say the word orbital? Yes. What does the word orbital mean?
The shape,
Yeah, the orientation.
yeah.
The orientation. So can you have a S atomic orbital? Is there such a thing as an S atomic orbital? Yeah. Can you have a P? Can you have a D? F?
Yes.
Okay. Hybridized orbitals, you don't have those. You have SP, SP2, SP3, SP3D, so on and so forth, blah, blah, blah. We could keep going, but you don't need to know the Ds. We can stop at SP, SP3. Can atomic orbitals participate in sigma bonds? What about hybridized orbitals? Can they be sigma bonds? Can they create single bonds? That's a single bond. Can you have pi bonding here?
No. Yeah. Yeah.
That's what this is, right? Can you have pi bonding here?
No.
No. So if you're just going to classify, kind of categorize, that's what you're doing. Single bond, double bond options exist for all atomic orbitals. You only get single bonds occurring on hybridized orbitals, and any double bonding character has to come from an unhybridized atomic orbital. Yeah.
So, like, with the carbon attached to the oxygen above example, the pi bond there,
Yeah.
is it not attached to the sp2 bond?
No.
So what's it attaching to? Like, what's it bonding with?
It is two, how would this look like? I need somebody's hands. Here, hold this. Yeah. Alright, here's carbon to oxygen. Look here.
What was that sound
Because we're just gonna hit you in the face. Here, hold that like this or something. So carbon to oxygen, sp2, sorry. sp2 hybridized, sp2 hybridized, interacting to make a single bond. Okay, hold that. Yeah. And then atomic orbital of carbon, an atomic orbital of carbon. Is this the S or the P atomic orbitals of oxygen and carbon? So is carbon bond in the S or in the P? P's. So unhybridized P atomic orbital, unhybridized P atomic orbital coming together to create some overlap.
But
So
even though
we're-
the p is being used in the sigma bond?
In the in the pi bond. So perpendicular, this is the internuclear axis, and this is perpendicular to axis. So 90-degree angle here, right?
But it still has the sigma bond,
The
right?
sigma is separate bond though. It's this bond.
Yeah, so that's the sp2
Yeah.
to the carbon
Yeah.
sp2.
Yeah. And this is totally separate. This is not somehow stuck in that bond somehow. It's not in there.
Well, and how do you have extra p, like, to connect?
Because you filled the valence shell here. You use the 2 electrons from here, or 1 electron from here and here, to create an overlap. That's full, 2 paired electrons. Now you have an unpaired electron and an unpaired electron, very unstable, they just want to be together. So they're going to spin pair, yeah, like this, but that bond is up here. It has nothing to do with this guy. He's not stuck in there.
Okay, so like in the graph
Yeah.
with the potential energies
Yeah.
and the levels, so it's like the one that doesn't have
Yeah, we didn't get there
like
today.
hybridized one?
We'll get there tomorrow. What time we got here? 14?
Yeah.
Yeah. Don't write this down, but don't write this down. Don't write it. But I don't want to leave that necessarily on a total cliffhanger. Here's what tomorrow will look like. If you take carbon and oxygen, there's 2 different elements. They both have 1s, 2s, 2p. Okay. You can create, this is the orbital diagram for like oxygen, and let's say oxygen, 2 oxygens come together. If you overlap along the internuclear axis, we're going to create a sigma 1s bond. If there's no overlap on the internuclear axis, we're going to create something called a sigma star. Do the same thing for the 2s. We'll have a sigma 2s, a sigma star 2s, and then this is where it gets a little crazy. The internuclear axis can still overlap to create a sigma 2p, or you can create 2 different, a pi 2p, there it is. You can create 2 different pi 2p orbitals and pi star, it hurts. And the sigma star. There it is. Got it. Okay, so to Gloria's point, if I have electrons here and the 1s, I can dump them into these orbitals. If we have electrons in the 2s, we can dump them into these. And then the 2p's can be dumped into here and here. So we're going to start drawing, this is a molecular orbital. This is the reality that general chemistry never told you is this is real, that's not. What we've been teaching you is for a single atom, and now when things come together, we create these molecular orbital situations.
Morgan,
Tomorrow.
I think